I know exactly what you're thinking. You've watched the first 2 episodes of the Git Virtual File System. It is incredible. Wouldn't it be cool if we could only pull back the covers and talk to the file system team and they can walk us through what it's actually happening behind the scenes? Is it a lot of stuff you've never covered before? Yeah. Is it a lot of neat stuff that we're lucky to be able to see? Absolutely. That's this episode of Dev Radio. Hi, and welcome to the next episode of Microsoft Dev Radio. This is part 3 of 3. We're talking about the Git Virtual File System that we have designed internally and have made open source. I'm here with Christian and Saeed. They were on the first 2 episodes as well. Guys, welcome back to the show today.
Thank you.
So the first episode, we kind of talked about the problem. In the second episode, then Saeed, you showed us what it felt like to be a developer using the system and being able to kind of have a transparent experience while you're using all the normal Git stuff you're used to. Meanwhile, behind the scenes, you have all this magic going on with the virtual file system. And so then we were at the end, and Christian, you agreed to come back, show us today kind of what it was like on the behind the scenes. You're going to pull back the covers, kind of show us what the file system is really doing, and in kind of and use as much nerd language as possible, I guess.
Yep, that's pretty much the plan.
Nice. I like your shirt, by the way.
Thank you.
I like the solidarity right now.
All right.
Good. Okay, let's back up just to our last episode, Saeed. Give me just the rough developer experience and recap what we talked about.
Sure. So the developer experience is you want to clone this gigantic repo, and instead of typing git clone and having to sit there and download hundreds of gigabytes of data the way Git normally wants to do, you type GVFS clone, and we download just enough data to be able to then engage GVFilt to virtualize your repository. But after that, you go into your repo and you run your normal Git commands. You know, you can git checkout, you can add, you can commit, you can run git status. All those commands work normally. Your IDE, your build all work normally because GVFS, in conjunction with GVFilt, will be able to pull in all the contents of the files as you need them, and none of your tools are any wiser.
Okay, so GVFilt is the MiniFilter, which is sort of what we're going to be talking about today, Christian.
That's right.
Tell us what a MiniFilter is. Not all of us work for the file system team.
Right. So Windows has the concept of a layered I/O model. So when an application sends an I/O request, like open a file, read a file, write a file, it conceptually sends it down a stack of drivers. And it goes down to the file system, and from the file system it goes down to the storage devices and so on. But between the application and the file system is the filter manager. The filter manager is a filter, which means that it sees I/O that's coming into it from the top, and it can modify it and send it back to the bottom, and then it can see the I/O returning back up through it. And what the filter manager filter does is it provides an API and a framework for other people to write little plugins called MiniFilters. And they're called MiniFilters because we have this older legacy model where a filter had to see every single piece of I/O going down and coming back up, and so it had to pay attention to everything, even the stuff it didn't care about.
Okay.
So many years ago, back in, let's see, it was first introduced in Windows XP Service Pack 2, I think. They introduced the filter manager, which allowed third-party developers like antivirus vendors, for example, to write smaller filters that plug into the side of the filter manager. And when an I/O comes down, the filter manager calls over, provides callbacks that the MiniFilter can use to filter the I/O. And the MiniFilter could just register and say, I only care about creates and reads and writes, which means it doesn't care about anything else, and so it doesn't have to see anything else.
Yeah.
So that's what a MiniFilter is.
Well, I was going to ask you, virus protection like Defender, that obviously is a perfect use case. What are some other MiniFilters that are out there?
We've got things like we've got compression, so to compress your stuff on the fly. We've got encryption filters. There are hierarchical storage management filters, which is actually the category that GVFilt sits in.
Okay.
And what that is, kind of the canonical example of that is where you have files that you need to keep around, but you don't need to keep them on your disk taking up space, and because, say, you only access them once a year because they're archives or something. And so you offload the file into some big old tape robot somewhere, and then you have a MiniFilter sitting on your system that says, that sees attempts to open these files, and when you try to open them, it pauses your open, goes off to the tape robot, fetches the content, sticks it on your disk, and then lets you retrieve it. And that's essentially what MiniFilter does.
I assume since they're so old, I mean, honestly, they've likely been tuned from a performance perspective, are probably as good can be. Yeah,
they're pay for play. Okay. Because they're MiniFilters, they don't interfere with anything that they don't care about. And these days, on a stock Windows system, you'll have half a dozen MiniFilters or more already loaded in the box, and the impact on performance is quite minimal.
Nice. Okay, let's transition over here. Now along comes the MiniFilter for your Git Virtual File System. Talk to me a little bit about the thoughts behind that.
So it's a MiniFilter, like we were talking about, and what that means is that, well, let me show you a picture here. So I have this slide.
Okay.
You can see kind of the entire layout of the system. You can see the VSTS cloud out here that holds all of your stuff. You've got the GVFS user mode file system that we talked about in the previous presentation, and the support library that we provide to it for it to be able to talk to the MiniFilter, which is shown here as the file system reflector, GVFilt. And so what GVFilt does is it intercepts calls from your app. This could be Visual Studio, the command line, Git, obviously. And it redirects anything that's necessary out to the user mode, which can then provide data back to the filter. And then the filter will cache information into the local file system, into NTFS. So we decided to go with a MiniFilter model because, like I said before, you get this pay-for-play thing where you can see only the IOs you care about, which turns out to be very important because we actually had an earlier prototype that simply reflected all of the I/O into the user mode, every single I/O into user mode, and it turned out that that was really, really slow. And so we decided that instead of doing it that way, we would go with this model where we would cache things locally into the file system and only reflect out to the user mode the stuff that needed to be reflected out.
Now, talk to me a little bit about that decision and why that matters. Fundamentally, what's the difference between kernel mode and user mode?
Well, it's not so much the difference between kernel mode and user mode. The problem is the transitions between the two. Those are slow. So the more you're having to go back and forth, the slower things get. And so if you're reflecting every single I/O you're doing, it's coming down from the app into kernel mode and then going back out into user mode and then going back into kernel mode. That slows things down immensely. And so by having this model where we simply send commands, the necessary commands out, and get the necessary data back only when we need it, that speeds things up a great deal.
And if I can add a GVFS perspective here, one of our performance goals was we know we're going to be slow the first time you access a file because we have to go to the cloud and download it, and there's all that overhead. But once we have the file already downloaded, we don't want that second access to that file to be any slower than normal. And so like the perf metric that we use is when you run a second build, a second full build, is that as fast as being on NTFS natively? So that the GVFilt approach is what allowed us to do that.
That's a pretty high bar. That's a pretty high bar.
Right.
Okay.
And by using, like I've said, I've mentioned that we use NTFS as a cache. That's exactly what that buys us. We reflect out to user mode and VSTS the first time, but all subsequent times it comes straight out of the file system. With that earlier prototype approach, it was always going out to user mode.
Yeah. You probably had some sort of cache, but you still had to do that transition between the two.
That's true. Yeah.
Okay. Okay, I totally get it. It makes plenty of sense. I like architectural diagrams that aren't crazy confusing. This one's great.
Good.
Oh, by the way, all of this that we see above user mode and inside the local scope here, that's what I install when I install your driver, right?
Yeah, you install this part,
Okay.
and it comes with this, and it also comes with this. This part gets installed as well.
Oh, of
so
course,
when you
because-
install the GVFS package, you get these three components.
Okay, that makes sense. Talk to me a little more about the approach around cloning.
So the last time, Saeed talked about how when you clone your repository, you use the command GVFS clone. It's the only time when you use a GVFS command instead of a Git command.
Okay.
When you clone, like you said, we pull down basically just the information you need to get started. And but on disk, when we lay out your working directory, we don't actually lay out the entire thing. Mm-hmm. And so I have a slide here that shows what the user perceives and what's actually on the file system.
Okay. Okay. So on the left, that's where it all begins, with just the bare bones.
In fact, right here at the top, this is the very, very beginning. When you first say GVFS clone, essentially what you've got is you've got this directory called your virtualization root, and it's empty. There's nothing in it. There's actually, in the case of Git, there's actually the .git folder. There's a little bit of .git metadata, but that's all laid down locally. As far as the files that you work with, there's nothing there.
Okay, and I remember that from the previous episode where Saeed kind of walked us through just these tiny little files that show up compared to what we would get these massive files otherwise. Okay, cool. And now, before you go any further, let me ask you a quick question. If I'm laying out my my Git repository, do I need to do anything special? Is there like best practice guidance that you would say, well, if you're going to use the virtual file system here, then you need to do this, or it's just play as normal?
Well, it's not so much, the requirements are not around using this virtualization solution. The requirements are more around the repository itself.
Okay.
Now, we're talking about the Windows repository, which, as we've mentioned, is gigantic.
Yeah.
And what GVFS allows you to do is to not get all of that stuff. But still, odds are that when you do a build, you're going to wind up pulling in a fair number of things. And so what we have, all the developers who work on Git were issued a 1 terabyte SSD, so that we have a nice fast storage system, and it's big. So if they're working on multiple projects and they create multiple repositories, they'll have plenty of space for all the repositories, for all the stuff that GVFS will pull down.
Okay.
But beyond that and a decent network connection, that's all you need.
Okay. Well, actually, that's pretty good news. And it's fascinating to think about. Like, this isn't a one thing solves every problem. It's neat to see even hardware can help really alleviate some of these. I mean, it's still a lot of data. Network connectivity is still an issue. There's still all this data you're going to have to pull down at least your first time when you do that initial build.
Mm-hmm.
Okay.
That's right.
All right. Now, talk to me about the transition from this first on the left side to the right side.
Okay. So like I said, we lay down this single directory, but what the user perceives is the entire thing. So if he goes into this root directory and he says dir, he's going to see a bunch of files. What he's going to perceive is this view over here in the lower right. So what I've got here is the blue are directories, the orange are files containing all of their data. This is what the user thinks he sees.
Okay.
Now, as the user navigates around in his tree, what actually winds up on the disk is more like this over here on the left.
Okay.
So these hollow blue circles represent what we call placeholder directories. These are directories that contain some of the files, but not necessarily everything.
Okay.
Like, for example, here, this dotted blue circle, this represents a virtual directory. This is a directory that shows up when you say dir.
Yeah.
But it isn't actually on disk at all.
And
There's
that's because
there.
inside it, there's also nothing there, and so there's no reason for it to be hydrated or whatever word you use. You don't say hydrated, do you?
We do. We say
hydrated.
But also the reason it's not there is because nobody's ever touched it.
Oh, interesting.
So you see this file here, this hollow orange circle, this is a file. This is what we call a placeholder file. This is a file that has at least had a handle opened to it.
Okay.
It may have been read, but maybe not. But it's been touched, and so there is at least something on disk for it, a placeholder.
Okay.
This is a file that you've modified. So all of its content is there. We call that a full file.
Okay.
And so on and so forth. All the dotted stuff is stuff that isn't really there on disk. All the non-dotted stuff is stuff that's been touched in some way, and so it's present on disk. But still, the user is presented the illusion that his file system looks like this.
All right, so when I'm looking at what is the, what's the performance change, looking at how many of those are just dotted circles, those are the ones that give me the most benefit. And then I suppose the ones that are the hollow circles, those are the ones that give me some. But if you look at it and then scope compared to the right-hand side, that is a lot of stuff that I don't have to go get.
Yeah. Yeah, and that's where the performance gain is the fact that as you navigated through your tree, we only pulled down these things. We did not pull down everything.
Okay.
And also, in addition to like pulling down and causing network traffic for the files that you're reading, the other thing that we do is on the left side there, all the files that are hollow are files that even though they're on disk, some of the ones that are solid but hollow, we're still hiding them from Git. And so when you run a Git status, it only has to look at the files that are filled in. And so on the left, you might think, well, half the tree is downloaded, right? They're solid lines, but only a small number of them are filled in, meaning the user has modified them, and Git only has to look at those files. So it's a double benefit there.
It's a huge benefit because I could have thousands of those hollow ones, and I can do a Git status, and it's nice and fast.
That's right.
Exactly. Yeah, so if I build some component, some, say, fairly sizable component like NTFS, file system itself. NTFS has a couple of dozen or so source files, but there's a bunch of other header files and things and other things that are involved in building it. So when all is said and done, when you build a component like that, you may wind up pulling down a few thousand files, but Git, like Saeed said, is only going to pay attention to the ones you modified, which might be 3. And so your Git status is much faster for it.
Okay. I see it, and I love it. That's really great. So, and if you didn't do it that way, then every time I said F6 or, I tried to build, all of a sudden I would spoil all the value of this file system.
Yeah.
Okay.
And in fact, our initial rollout of GVFS didn't have this feature of, initially Git would have to look at anything that you had read. And so users' performance would slowly get worse and worse over time because every time you build something and you hydrate more files, now Git has to look at more files. So that we had to do this, what we call O-modified, make it so Git only looks at what you've actually touched to keep the performance good.
Okay.
Yeah.
It's well thought out. I like it. All right. Keep going, Christian.
So I thought I might talk a little bit, now that we're talking about the filter, I thought I might talk a little bit about what actually happens, what the filter does when you read a file. Because I've mentioned that a file gets recalled by getting read. So as a simple example, if you use the DOS command type, that spits out the contents of the file to the console, if you say type foo.txt, then the file system operations that happen, there's an open, and there's a read, and there's a close. So when you very first begin, like I said, your root directory is unpopulated completely. And so what happens is the open goes down the stack, GVFilt sees it, and well, what actually happens is the open goes all the way down to the file system, and the first thing that happens is it bounces off what we call a reparse point.
Okay.
And this reparse point exists on your root directory. And a reparse point is basically just a little tag that identifies a type and some data. And what happens when the file system encounters a reparse point is it bounces back the open call and says, I hit a reparse point.
I see. And
here's the contents. And usually what happens is that a MiniFilter is registered to own that reparse point. And so that's what happens in this case. GVFilt, when the open comes back, it sees, oh, hey, he bounced off one of my reparse points. I need to go to GVFS and say, give me the data for this file, for this directory. And so GVFS says, okay, here's the data for that directory. And then GVFilt turns around and says, okay, now I've populated this part of the path. Now I need to go and populate the next part of the path, and so on and so forth until you finally hit the end of the path. And as you're going through this process, you're laying down on disk all the intermediate directories until you get to the file you're actually interested in.
I see. So it's root directory, subdirectory is another point, and then subdirectory of that's another point, and the subdirectory of that's another point, and then the file you're asking for in the first place is the final point in there.
Yeah.
Okay.
And so eventually the file itself gets a placeholder laid down for it, which is just basically the metadata for the file, but not the contents. And then at that point, the open is done, and a file handle gets returned to the application, to the type command. And then the next thing type does is it says, okay, I've got this file handle. Now I want to read. So it reads from this file, but this file doesn't have any data in it. And GVFilt knows that because it knows that the file is what we call partial. And so it turns around and says, hey, GVFS, give me the data for this file. And GVFS goes and gets it and writes it down straight into the filter. And the filter goes and sticks it on the disk, and then it returns the data to the caller and says, here's the data you asked for. Now the caller, he has no idea that any of this is going on. All he sees is read, data comes back.
Now, when I do that, and you know, when I'm building, let's just say there's 10 files instead of the thousands of files, and I ask for those, is that 10 individual calls, or is somehow it being batched together and being handed off to the MiniFilter all at once, or you tell me?
Well, what the build engine is going to do, what the compiler is going to do, is he's going to open a file, he's going to open a source file, he's going to read the contents of that source file, and he's going to do that individually. So he's going to open, read, open, read, open, read, open, read. And so that's what the filter sees. He sees all these different reads to these different files. And of course, the filter at his level, he doesn't know anything about this higher level logic. He doesn't know that the compiler is opening a bunch of files, and then he's going to synthesize the contents together and so on. All the file system sees is open, read. He doesn't know that they're connected.
Okay, so that's a good point. So I'm inside Visual Studio or whatever, and I hit build, and I get all of these things. I could also be, like Saeed showed us in the last episode, I could be in a command line and just say type file and see it. And you're just saying the filter doesn't know which one is which.
Yes, he doesn't know.
And you wouldn't want it to, right? Because then you've got all these dependencies you wouldn't want to have to fiddle with.
Exactly.
Okay.
Yep. So then now if you type that file again, GVFilt doesn't have to do anything, because when he read the data out of GVFS, he wrote it to the disk, and now
which
it's
changes
cached.
the pointer and or the bounce pointer. No, I forgot the word.
The reparse point.
The reparse point. Yeah.
Yeah.
Nice.
Yeah. So when we see an open to that file again, we don't see these reparse bounces to the intermediate folders because they're already hydrated. They're already on disk, and we don't see the reparse point, the reparse bounce on the file itself because it's already there, and so we don't have to do anything. And when you ask for a read, we don't have to do anything there either because the file is already on the disk, so it just reads the way that it normally would, as if we were never involved in the first place.
Perfect. So I still have the MiniFilter there if I need to go get it from, you know, that code that's in user mode. But like your architecture diagram before showed, if it's already there, I stay down below that line. Don't have to worry about the cost of transition to that other mode. Everything, it works like it's a real file system. Like everything is just there, and I get the speed that I would expect.
Yeah, because you are talking to the real file system.
Yeah, because I am. The reason it treats it like the real file system is because it is the real file system.
That's right.
Got it. Okay. All right, cool. All right, I follow it, and it's well thought out. What else do you want to show me?
So I've mentioned a few of these state names. I've mentioned virtual files and placeholders and full files and so on. So I wanted to tell you what those actually are.
Good, yeah.
They represent the life cycle of a file from the time it's projected to the time it's deleted.
Okay.
So a file starts off being virtual. It's not on disk at all. It's projected during enumerations of its parent directory. That is, if you type dir at the command line, you see a bunch of files. Some or all of those files might be completely virtual. That is, the data is being provided by the user mode provider, by GVFS, and the filter is inserting it into the results of that enumeration. And so you see them even though they're not there.
Okay.
Now the next state that a file can have is a placeholder, and I've got a slide for that.
Okay. All right, I can see your slide.
So you can see here I've got file and placeholder. So placeholder is the one we're going to talk about right now. So you can see for both of them, you've got metadata, you've got potentially alternate data streams. But for the placeholder, the primary data stream, what we usually consider as the file itself, the contents, there's nothing there. It's what we call sparse, which is a mechanism that NTFS provides to allow you to say, hey, this file is yay big, but it doesn't actually have data in it.
Okay.
Databases use sparse files, for example. Say you have a 1 terabyte file, but big ranges of it are actually empty. So the file system saves space by only providing allocated blocks for the data that's actually present. So we take advantage of that mechanism because we need to report things like the size of the file, even if we haven't retrieved the data yet.
If I have a, let's just play with numbers. If I have a placeholder that's a terabyte in size, what does my hard drive think?
Well, if no data has been allocated to it, if we haven't actually recalled the data to it yet, the placeholder will say that it's a terabyte in size, but the entire placeholder actually fits inside the MFT. It's probably like 1K.
Right, tiny. Okay, so it'll look like, that's actually pretty great. I could theoretically clone a gigantic repo and 2 or 3 times and not take up 2 or 3 terabytes of space.
Yeah, if placeholders have gotten laid down for them and we hadn't retrieved the data. Now, of course, we go one step further, like I said, because we only pulled the placeholders when you actually touch the file. We don't go and lay down a bunch of placeholders up front and then fetch the data. We only lay them down when you ask for them.
Yeah, even better, even better. Okay, so we've got the first type, which is the virtual file. Then we have the placeholder. Let's go to the next one.
So then we have a hydrated placeholder, which is the result of reading a file, and it's the result of that process that I described before, where we fetch the data and place it on the disk. And so then a hydrated placeholder, it looks like this placeholder, but it's got the data stream populated, and it still has the reparse point on it because the reparse point contains a little bit of extra metadata that GVFilt uses to keep track of things.
Okay.
The next state it can have is a dirty placeholder, like if you change the metadata, like the timestamp, for example. And what that does is it makes it so that the on-disk cache, or the on-disk file, is no longer a cache of what's stored remotely. There's a disconnect now between what's remotely stored and what's locally stored.
So now you're actually going to update the Git system as well, or the Git information.
Yeah.
Once it's a dirty, hydrated file.
Yeah, once we've touched it, Git starts paying attention to it. You start tracking it.
And now, when I have that, when I go from metadata to a hydrated file and I'm pulling in that file stream, what's the user experience? You know, if that's a pretty large file, it just kind of locks like a normal GET request would, where it's just big and you got to wait for a second.
Yeah, that's basically it. Like if I say, for example, I have a very large source file, megabyte or something.
Sure.
And I just open it in Notepad. What I'm going to see is a momentary pause. Notepad's going to take a little bit longer than normal to display the contents of the file. But then it gets displayed and everything happens as normally. If I close Notepad and then reopen it, you don't see that pause anymore.
Gotcha. And that initial momentary pause is going to, the duration of that pause is going to be based on the file size, my network bandwidth, everything like that.
Yeah.
Okay. Okay, cool. Yeah, that makes sense. You would expect that. I mean, this is real data. We have to actually get it.
Yeah.
Okay. Okay, so now I've got my dirty hydrated file. That means for whatever reason I've gone in and changed something, either a property on it or its content.
So its content actually makes it what we call a full file if you change the content. If you open a source file and you edit it. So again, that makes the file no longer a cache. And any file that you also create locally, like say you create a brand new file on your disk, GVFilt also treats those as full files.
Okay, sure. Yeah, because there's no cache in the cloud yet.
Right, and they look like this thing on the top. This is the normal state that a file has, and you'll notice the reparse point is gone. We take it off. If it's a full file, it's no longer GVFilt's problem anymore. Okay.
Makes sense to me.
Okay. And the very last state that a file can have is what we call tombstone. And this is one that I wanted to demonstrate.
Yeah, tombstone, okay. Okay, as Christian pulls that up, Saeed, there's a lot of moving parts here. How did you manage the complexity?
Well, it's been an interesting process. The nice thing is that GVFilt is doing a lot of complex things under the scenes, under the covers, but the interaction up to user mode is actually not as complex as you would think. The basic interaction from GVFilt to GVFS is really 3 things. GVFilt will ask us enumerate a directory, and we'll give it a listing of the contents of that directory. It'll ask us, I need placeholder information for a file, or it'll ask us, I need the contents of a file, and we'll deliver those details. So as far as like projecting the virtual file system up in GVFS, that's all we have to care about is just the shape of the tree. There's additional complexities in like when a file is first modified, we get an event from GVFilt to GVFS, and then we have to go and update Git's data structures, and there's a lot of complexity there, and that the way we manage that is with lots and lots of functional tests to hit every corner case of what Git might expect, and so that's been a challenge for sure.
Yeah, and the risk is high, right? I mean, we're using this internally as well. We want this not only to work well, we want it to work right, and
that's right.
We can't tolerate. There is no toleration. I mean, if we were to lose data,
that's right.
I don't even want to think about it. It's terrible. All right, Christian, yep. I could see your screen. I could see 2 command prompts you pulled up.
Mm-hmm. Yeah. So what I'm going to do is I've got this little application called GVFilter Test App, and what it is it's a dummy GVFS provider. It serves the same purpose as the GVFS system it has, except all it does is, for its backend, instead of VSTS, it uses a directory we call it the layer, and what it does is it makes it look as if the contents of the layer, live inside the scratch. And so I'll show you. The layer has some files and a folder and another file in it.
Okay.
And the scratch right now has nothing.
All right.
Okay?
Gotcha.
Now, by the way, the reason we call them layer and scratch is these are terms borrowed from containers, Docker containers, because the GVFilter filter itself is actually a fork of our container filter that we use for Docker.
Oh, that is awesome. Nice. Nice. Good connection. Good connection.
So I'm going to fire up over here on the right, by the way. So I'm going to go into the scratch directory. You can see nothing up my sleeve.
Totally empty.
Nothing here. Even if I say /a, there's nothing hidden.
All right.
So I'm going to fire up the GVFilter test app. Okay.
Right.
So the GVFilter test app is up. Now what this has done is it's opened a communication opened a communication port to the filter, and it's ready to receive commands from the filter.
Okay.
So now over here, I'm going to do a dir in Scratch again, which you saw was empty.
Totally
now
empty.
It's not. Now you see over here on the left window, my provider spit out information about what the filter acted.
Mm-hmm.
The filter said, start a directory enumeration, get me the enumeration information, and then what the provider said is it said, okay, this is what exists in the layer.
I see.
In this.
All right, wait. All right, so you can see there's nothing in the scratch, and then you can see there is, but let's be honest, one magician to another, there really is nothing in Scratch.
Right. If I quit the provider and I go back and I do a dir again, there's nothing there.
Yeah, yeah.
Because everything in this enumeration was provided by the provider.
Sure.
So fire up the provider again. So what I'm going to do is I'm going to scroll the output so that you can see the output of an individual command.
Okay.
So now, there we are again. The files are back.
Mm-hmm. And I can
now,
see
what
it's
I'm going to
reacting. All right.
I'm going to show you what happens when I type a file out, like we walked through. So I'm going to type out baz.txt. So I've got content.
Yeah.
Now over here, you can see there's also directory enumeration stuff happening because CMD, the way that it finds the file that you asked for is by issuing the find first, find next, Win32 APIs, and those are directory enumeration APIs.
Okay.
So it's saying, find me baz.txt. Here it is. There's baz.txt. And now this is get placeholder information. This is the type command saying open the file. Now, GVFilter has intercepted that open and has turned around to the provider and said, hey, I need the metadata for this file. Get me the placeholder information. And so the provider...
Okay, but because you said type, then getting just the placeholder information, that's not enough, is it?
That's right. All we've done is, you can see the provider here is saying, I've opened the file in the layer, open layer baz.txt.
Mm-hmm.
I'm creating the placeholder. There's the placeholder creation. And we also report back, who caused placeholder creation. This was something that we added in the filter a while ago because we were trying to track down who was causing all these files to get hydrated when we didn't expect it. So we tell the provider now, this process hydrated the file.
Sure.
So that's type's open call. Now type sends a read call, which GVFilter translates into a get file stream command. So he says, hey, give me the file stream. Give me the contents for baz.txt.
Mm-hmm.
And this is information that he uses, this epoch and content ID. This is metadata information that allows a provider to change the contents. Like say the file changes on the back end. This allows the provider to know whether the file that he's being asked for is stale, and so he can take actions to make updates if he needs to.
Oh, I see. Yeah.
So here's the provider saying, okay, I'm going to open the file in the layer, write to placeholder triggered by GV write file. So he's saying, write the content starting at the beginning for 62 bytes, status success.
Got it. So that line and the line before it, in that whole workflow, that may be the most expensive set.
Yeah, because here we're actually getting the data and we're sending it down into the filter, and then the filter takes that data and he writes it into the file system.
Gotcha.
And then he completes the read. And this is just the end of CMD doing his, find the name processing.
Okay.
And it turns into type getting the contents. This is the content for baz.txt.
Now, if you were to turn off on the left, if you were to turn off the test client, and you were to do a dir again, there would be a file inside our Scratch folder.
And there it is. Yeah.
Yeah. And it's actual. It's not just a placeholder. There's content in there, the whole shebang.
Yep.
Right. Because you had to actually do it. I get it. I get it.
So we'll start up our provider again.
Okay.
Scroll past this. Now what I want to show you is I mentioned tombstones.
Yeah.
Tombstones are a way of hiding a file from an enumeration. So like you saw, when we do a dir, the provider returns back all the files that it knows about.
Mm.
But if we deleted a file on the local end and we did a dir, we wouldn't want it to show up again, which is what would happen ordinarily, because GVFilt would say, hey, give me the enumeration. The provider would say, here's all the files that I know about, and GVFilt would say, here's all the files.
That's a good point. Yeah, that is, okay, I follow the problem.
So what actually happens is GVFilt kind of does two enumerations. He enumerates what's on the local disk, and he asks GVFA, he asks the provider for the enumeration, and then he merges the two together. And anything that's locally present overrides whatever the provider said. Because say that you wrote to a file and you extended its length.
Yeah.
Why don't I do that?
Okay.
Echo some more content, append to baz.txt.
Sure.
Now you see on the left, the provider said, hey, baz.txt has been modified.
Mm-hmm.
So he saw the modification. So I'm going to scroll that past so that you can get a nice clear screen.
Okay.
And now if I do a dir again, sorry.
Okay.
Baz.txt is now 82 bytes long. It
Yeah.
used to be 62 bytes long. But it hasn't changed on the back end. The back end version of baz.txt is still 62 bytes long. So the local Baz has overridden the remote Baz in our enumeration.
Right. It always has to be the one that it prefers.
That's right.
Now let's talk about foo. Now the thing with foo is it does exist in the cloud. It's 62 bytes long as well. And you know that in your source code we use foo. We haven't hydrated it yet. It's just a placeholder,
right.
Or it's not even a placeholder right now.
It's nothing.
But you're about to delete it. Now what happens?
So I delete foo. So let me get this here so you can clearly see what the provider does.
Okay.
Del foo.txt. Zap. Okay, so over here on the left, you see open file, create placeholder. So what the delete command actually does, what the delete API actually does, is it opens a handle to the file.
Okay.
It calls the set information command to set the delete disposition for this handle, which makes it so that when it closes the handle, the file system deletes the file. That's how delete actually works in Windows.
Oh, really?
Yeah.
So it just marks it to delete, sort of.
Mm-hmm. Exactly.
Huh.
So delete's kind of a side effect. So you can see here, the provider sees the open. He creates the placeholder for it. And then we see pre-delete.
Yeah.
So remember I talked about the layered file system. I/O flows down and it flows back up from the file system. So when it's flowing down, we call that the pre-operation. And when it's flowing back up, we call it the post-operation.
Okay.
So in the pre, we see this set information call. And we see that it is a set delete.
Okay.
And so GVFilt treats that as pre-delete. And so it makes some changes in its data structures to get ready to delete the file. And then we see this. This has come from the post. Actually, this has come from the post cleanup. In other words, the set has come down, gone back up, and then the close, which we call cleanup internally, the close has come down and has come back up. And the file system has notified the filter, the result of this handle close is I deleted the file.
Perfect. And then you don't even hand off to the virtual file system now. You're like, don't even mess with this. We've deleted this file.
Well, actually, we notify the provider that it's been deleted, so they can take any actions it wants to. But if I enumerate the directory again.
Now, the purpose of notifying it, just out of curiosity, is because you want to make sure that the client updates the Git information so that it will remove it from cloud whenever I do a commit?
It's not so that you'll remove it from the cloud. It's so that we basically from GVFS and Git's perspective, a write to a file and a delete of a file are the same kind of thing. It's like you modified a file, and so now Git has to consider that file when you run git status. And so when you run git status, if you wanted to find that this file is missing and show it to you in the output, we have to add this file as a modified file when you delete it.
Got it. So when I look for changes, I want it to show up when I'm looking for changes. And whenever I do my final commit, I want that to be...
That's right. When you do a commit, Git will find that it was missing, and it'll record it as a file that was deleted, and then everything flows from there.
Yeah.
Okay.
Yeah. But that's why we tell the provider, hey, this file got deleted, so that the provider, GVFS in this case, can take those actions. It knows that it's been deleted, and it can go and update the Git metadata.
Okay. Now, I saw you just did another dir on this folder, but I see all three files on the left.
Yeah. You see that foo.txt is gone from the right. We deleted it. But you see on the left, because we requested an enumeration, it still exists in the back end. It still exists in the layer. And so that's what the provider says. There's foo.txt. But clearly, for some reason, the filter is smart enough to know that it shouldn't show up anymore.
Ah, yeah.
And we could do that by simply remembering in memory that we did that, but that would quickly get...
You can't scale that.
Yeah, exactly. That wouldn't scale. It would get out of hand quickly. So let me kill the provider and show you what's really going on. Okay, so I've turned off the provider.
Okay.
Now I'm going to do a dir/a because I want to show you where foo actually went. Well, there's baz.txt that we typed out before, but there's foo.txt.
I see it.
But you see that CMD is marked it as a junction because that's what CMD calls all reparse points.
Oh, I see. Okay.
What's actually happened is that we have laid down a tombstone for foo.txt. We've laid down a special reparse point that makes it so that GVFilt hides the file. So remember I said that when you do a dir, we actually enumerate the local disk and we ask for the remote enumeration and we merge them together. In that merge process, if there is a tombstone for a file, that causes the file to get deleted from the enumeration. We suppress it from the enumeration.
Mm-hmm.
And that's how we manage deleted files.
And if I had already hydrated foo, is this version of foo still just a placeholder with the delete information?
Yeah. In fact, I'll show you. So we're going to fire up the provider again.
Okay.
Let's delete baz because we know that baz is actually locally present on disk.
That's right. And we know that it's 82 bytes.
Uh-huh. So there you see on the left, we see the same output from the provider. It's been deleted.
I do.
So turn off the provider again. I'll show you what's happening on the local disk. We put down a tombstone for baz.
Yeah.
The reason we put down a tombstone for baz is because there's still a baz.txt in the back end. So we still need to suppress it from showing up.
And its file size, let's say baz was not 82 bytes, but 82 megabytes. In this case now, it's a tiny little placeholder, just metadata.
Exactly. The file was actually deleted. So what we actually do is the delete actually happens on disk. But then after the file is removed from the disk, we go and replace it with a tombstone as part of that operation. So
makes plenty of sense.
Yeah.
Now, hey, I'm curious. What if you try and undelete baz now?
Well, undelete is actually not a thing.
Oh, okay.
Not in the file system, right?
Exactly. See, at the file system level, there is no such thing as an undelete. When you delete a file in the shell, for example, it actually goes to the recycle bin.
Yeah,
which,
that's right.
from the file system's perspective, what it sees is a rename. Because you actually rename the file into the recycle bin. And if you undelete it, what you're actually doing is you're renaming it out of the recycle bin. And the recycle bin, as far as the file system is concerned, is just another folder.
Got it. And without the shell, a delete is an actual delete.
Yes.
Okay.
Now
so,
that said, from your git command, you can undelete, right? Because what you can do is you can say, you can undo any change because you've got all the history there. And so in your git command, you can now say git checkout -- baz.txt. And what that'll do is it'll restore that file back to the state that it was last in your last commit, right?
Good,
and so, because we saw, the GVFS saw the delete, and we told Git that this file exists, when you run that command, Git will treat it like a normal file, and it'll restore that file back to its last state.
Got it. So I can't undelete at the file system, but really who cares? What I would really do is undo my changes in Git.
That's
okay.
right.
Makes plenty of sense.
Yeah, because undelete is always a higher level concept implemented by things above the file system. Git, shell, whatever.
Okay. All right. So I'm with you now. I see the two junctions, and keep going.
Well, that's pretty much it. That's how Git, or how the filter communicates to the provider. It's how the filter handles deletes, masks out things that the user should no longer see, even though they're still there in the back end.
Now, what removes those junctions? Like when I do a commit?
Well, that depends on the provider. In the case of GVFS, yeah.
Okay.
The filter, the user mode library that we provide, that GVFS plugs into, the way that we provide the API for the filter, it provides commands for the provider to directly manipulate our tombstones and our placeholders and stuff. So say, for example, you check out a new branch. Say that you've deleted foo.txt.
Yeah.
And now you check out a new branch that has its own foo.txt. As part of that view change, the provider goes and updates everything, and it goes and deletes that tombstone so that it's no longer present. And then when you do a dir again, you see the new projected foo.txt, and the whole thing starts over. You know, you start from virtual file, you go to placeholder, etc.
Yeah, and then branching and moving back to a previous commit, and wow, there's so many moving things here. I'm impressed that it seems so simple. Of course, my experience, I would never see that left screen, right? Everything's to the right. Feels like I'm just interacting with the file system in a normal way, which is kind of the beauty of the whole thing.
Yeah, exactly.
Yeah, it's fantastic. All right, so great, Christian. I can tell that there's some love that's gone into this to make this work the way that it has. Saeed, when I'm considering this in my, I assume this side of it is always on the client. The other side that's up in VSTS, we've already talked about how it's so transparent to the user, and how we're pretty close to providing an actual production version to developers.
That's right. Yeah, we're just kind of putting on some finishing touches, and you know, it'll be ready for prime time. I mean, the fact that the whole Windows org is already using it shows you that the quality is there, and people are successfully using it. So we're almost ready to go.
That's beautiful. What do you think? What do you think V1.1 is going to have that V1 doesn't have today? What was on your dream backlog that you had to pull off?
You know, really, it's just performance is the #1 thing. You know, we keep going after more and more ways of making the performance better. You know, like you saw that, you know, when you open a file the first time, there's a slight delay when you open it, and you know, there's things that we can do to be smarter about prefetching the data that we need before you need it, so that you don't see the delay, right? And so we're finding better ways of optimizing all of those things to make your builds faster, to make your Git commands faster. And so that's our biggest focus right now, is just continuing to make those things more performant.
What would be the way I would do that? I would maybe somehow mark assets up in Git as this is really important. Get this no matter what they're doing. Don't virtualize this one.
That's certainly one way. I mean, you wouldn't do it necessarily in Git itself, but you know, the avenue that we're looking at is, like, you run a build, and the build has a lot of information about what files it's going to read, and if it has a channel to communicate that to GVFS, GVFS can start downloading those things up front, and so that the files arrive before the build tries to open them. And so you can kind of set up a pipeline there where the contents show up just before you need them, and then the file I/O doesn't slow down.
Nice.
So that's an example of one way we're thinking about optimizing.
Yeah, that'd be a nice clean way, and kind of stick to the. Sounds like you have kind of a philosophy of don't change the developer's workflow as much as possible.
That's right.
So
that's right.
I definitely like that. And okay, so Christian, I don't know how often a regular developer gets to sit down with somebody like you, honestly. That 18 years with the file system. I imagine
15. I'm not that old.
50 years with the file system.
15.
Oh. All right. So, but even still, many years with the file system beats what most people have as far as experience with it. It's neat to be able to see kind of what the capabilities are under the hood, how things like this, partly because of other scenarios that it's a Git Virtual File System isn't the first thing that's tried to do virtualization of a file system, and to see that these mechanisms are already there and you can tap into them, and performance was already a consideration, and all the things are there and easy to use. Meanwhile, it remains mostly transparent to the end user so that you can add all this functionality. To me, I'm a fan of Windows already, but it's neat to have that confirmed, that it's not just, blind love, but at the same time it's pretty cool. And a lot of smart people are involved to make it pretty clever under the hood. Pretty good. Thanks for showing us the virtual file system. If you're a developer and you're watching this right now and you realize that Git is inevitable and your company maybe hasn't gone that way yet at all, and one of the things you're concerned about is the size of your repo, then isn't it nice to know that you're not alone and that solutions are already being made by people who know what they're doing, and this is it, the GVFS. Now, Saeed, tell me where you would send a developer who wants to learn more and just read up on this like crazy.
Sure. We have a website, gvfs.io, and from there you can find information about GVFS. You can find a link to the repo on GitHub because all the code is available there. That's the starting point for all the information that we have.
The whole thing is open source on GitHub. Now, to be clear, you and I talked a lot about Visual Studio, or the VSTS, up in the cloud, as it enables this already, but it's not limited to that. I can use this if I use other systems?
Well, any service that chooses to implement the GVFS protocol will support your usage of GVFS against that service. So right now, the only service that supports it is VSTS, but the protocol is open, and I know other services are in the process of building support.
Okay, and this feature is going to roll into on-premise TFS?
That's right.
All right, that's good.
Yep, the next release of TFS on-prem supports it as well.
All right, even better. This is cool stuff, really cool stuff. Guys, I can't thank you enough for walking me through this. Explaining the problem alone is daunting, but being able to see the solution, pretty inspiring. Saeed, thanks for being on the show again.
Thank you.
Christian, thanks for coming back and walking us through the innards of this solution.
Thanks for having me.
All right, guys, have a great day.